then calculate and then calculate the output variable with that random initialized weights. Then what would be the error we calculate, and then we do the same for the second data point, and then we do the same error calculation for the third data point as well. That is, for this one, let us say I am writing it as training steps. First, what we do, calculate, sorry, initialize weights, initialize our initialize weights or parameters, and then get prediction. Third, calculate error. Fourth one is adjust parameters or weights. Fifth is again prediction happens with the adjusted prediction and predict with the adjusted or modified weights. This process continues until we reach, in theory, we say that we should have closer to zero error. But what happens in reality is, let us say, and one more thing I want to clarify here, till this point, from here, this point to this point, adjust parameters. This we call it as one epoch, EPOCH. One epoch or one pass, you can say. In single pass, what we do is we initialize the parameters, we get the prediction, we calculate the error for that prediction, and then adjust the parameters or weights. Basically, one prediction if we do, then it is one epoch, one iteration, you can say. But usually in that one prediction or one iteration itself, we will be adjusting the parameters according to the error that we get for our initial prediction. So that is why they came up with this word called epoch. Otherwise, it is just an iteration that we do. So once we do this one, next after adjusting the parameters, we will predict the output variable again. So if I draw the graph between number of epochs and the number of error, let us say on x-axis I have number of epochs, on y-axis we have error, which is usually we represent it by capital E. So as the number of epochs or the number of iterations increases, our error should come down like this. It may or may not become almost like it will be asymptotic, in the sense like it will be almost touching it, but may not become zero. But usually, this is theoretical. But usually what happens is, this fall or the curve, the path it follows when we increase the number of epochs or the number of iterations for adjusting weights and then predicting the output, what happens is, it may not be very much like this. It may be zigzag as well. And after certain time, it will become like almost flattened. It doesn't increase. It doesn't decrease much, this error, after certain number of iterations. So at that point, what it is practical to stop the training, right? Because this is what we can achieve. This is what is the lowest uh, possible error rate that we can achieve for this particular data set with the given conditions, like with the whatever the initial conditions that we had defined, like initialize the weights, right, randomly. For that randomly initialized weights, this is what we can achieve. What is the point of using computing resources still, even though your loss is not decreasing or the error is not decreasing? So that is where we will stop. So why I am talking about this now is because you will have the question, right? Again, we will predict with the adjusted modified weights. How long you will adjust or predict the output? It is till this point. And one more addition to it is here when we are predicting, when we are uh, initializing the weights and getting the prediction, how do we do? For example, here I have three data points, right? So usually first step or the initially what people used to do is, for this they will predict, let us say the prediction is 20 for this one. I am just writing it as, yeah, otherwise let me write it here. So we had initialized the weights and then got the predictions. It is 20 and this is around 45 and this is around 60. Okay. So here again, one more thing, let me make it more clear. Initialize the weights or parameters, it may not be so clear to you as of now. Let us say here it is 135 and 30, 50, 70, and this is being like initial data point. We assume that the underlying pattern is something like a curve. That is, here it shows independent variable experience and it is salary on dependent axis or y-axis. So when it is zero, its experience is zero, salary should be zero. So you can make it passing through origin also. But as of now, let us consider this is the point. And when the experience is one, we have some salary of 30. And when experience is 50, 3, it is 50. And when experience is 5, it is 70, something like this. So it is following a linearly increasing pattern. So underlying line equation that we need to calculate, that is something like y equal to mx plus c. This is the equation that we need to identify what is the slope and what is the intercept. This intercept is c, right? Usually in line equations. Basically, we need to come up with this m and c that best fits the given data set. These are the parameters basically. M and C are the parameters here. Or for that matter, you don't need to even worry about what is slope, what is intercept also. You just need to understand that if your data set is following linear fashion, there is a linear pattern that is present in the data set, then you can assume any generic equation. Y is the output variable, and if x1, x2 are the inputs variables, or let us say just you have only one input variable, like the example that I shown here, that is x only, then you can say anything like ax plus some constant term that can consider this, that okay, if you don't take that constant term, issue is that you are always assuming the data set it is passing through the origin. So to make it more generic, to so that we can generalize it to any data set, we are assuming that there is a constant b present here, so that we can shift it in case during the training, if it is passing through the origin, it's okay, it will become zero, this parameter. else it would be there, and it can come here also, like this. It can come here also, so that it is generic. So generic line equation, this is right, y equal to mx plus c. That is why I was talking about. Or else you can assume, yeah, if you are not so comfortable with the terminology, with slope and constant or intercept, you can assume any generic line equation as well, which looks something like this, x plus b. And if you have multiple inputs, then ax1 plus bx2 plus c plus c. This is another one. So you can assume any generic equation, and this A, B, C are the parameters here, are the weights. Here A and B are the parameters. These are the things that we are trying to calculate now. Hope this is clear. Now let's go back here. So we had initialized random values for M and C, are A, B, coefficients are the parameters, are the weights, and then calculated the output here in the initial pass, 20, 45, 60. Then what we do is we calculate the total error here. That is, sorry, we have not calculated the error yet. This is the prediction, right? And error, this is, it is up to you. You can consider y actual minus y pred, or y actual minus y pred, anything. Or usually people consider it as y actual minus y pred. So we will consider the same thing. So it is 30 minus 20, that is 10. And 50 minus 45, it is 5. And 70 minus 60, it is 10. So we calculate the total error here. Let me remove this. So 10, 10, 20, 25. This is the total error. So what we are doing here is, for one initialized weights, we are calculating error for each and every data point. Error for each and every data point, for this, for this, for this. And then calculating this total error. Then we are adjusting the weights. This is called as vanilla or plain gradient descent. Why gradient descent? I will talk about it later. And another approach people follow is they calculate error for one data point, for this one data point alone, 10 data point. Sorry, that they got 10. Then that's all. They will adjust the weights. This M and C, initialized weights. That is called as stochastic gradient descent, SGD. So here for each and every data point, we calculate the error, we adjust the weights. We calculate the error for the next data points, again we adjust the weights. If we are doing that, then that is called as stochastic gradient descent. But here in the first plain gradient descent, what we do? We calculate the errors for complete data set. That is, we accumulate the errors. That is the proper word. We accumulate the error for complete data set for one iteration or one epoch, and then adjust the weights. We don't adjust the weights after calculating error for each and every data point there. So that is plain gradient descent. And another approach where we adjust the weights immediately after calculating error for single data point. That is stochastic gradient descent. Another approach is mini batch gradient descent. So where we will split the data set into some batches. That is, I am removing all of it. As of now, we don't need everything. So let us say I have some 1,000 data points in my data set. That is 1,000 rows in my data set. Then what I do is I can split it into 100 data points of 10. batches, we say. This is batch, 10 batches. For each batch, I will calculate the error. I will accumulate the error and then adjust the weights. Then that is called as mini batch. So you can simply write it as something like don't split complete data set, then it is plain. If each and every data point, you adjust the weights, uh, you calculate the error and then adjust the weights, then it is SGD, stochastic gradient descent. If it is batch wise, then it is mini batch. That's all. So here only point that you need clarity now is how do we adjust the weights? That is where this gradient descent comes into picture. So now let us take this further. Till now, any questions you have? Okay. So for this one, for this particular use case, you need to speak up. If you don't understand, please do ask. If you keep quiet, I don't understand whether you are able to cope up with the concepts or not. So yeah. So here for this particular use case that we are working on right now, it is a regression use case, we call it, because here the prediction output target variable is a numerical value, right? 30, 50, 70. And we need to come up with, for a given, let us say next, they come up with 2.5 years of experience. Then what would be the salary? If this is the problem statement that we are working on, then the output or the target variable that we need to predict is a numerical value, right? So these kind of use cases are called as regression use cases that we discussed in the last session. So for this kind of use cases, the error is usually we follow is squared error, that is y minus y pred whole square we do. It is because of as I mentioned earlier, we don't want to do that non-differentiable function which looks like this or like this. I'm not sure, but yeah, anything is both of them are non-differentiable at this particular point, right? So we prefer functions which look something like this. Smooth transition should be there, all of it. So like y rather than y minus y pred, if we do this y minus y pred whole square here, then the function become parabolic. That website, I missed to check it out. Graph. Um, figure out. Uh, visual algebra. Not, I forgot that website actually. You can just give the equation, it will create the graph for you. Uh, this not Desmos finally. So here y is the variable and y pred is some constant, right? So you can say uh, here it follows the same convention x and y. So I am not giving y here. I'll just give it as x only, so that it will be same x minus something like 2 whole square. So we can follow the same convention x minus 2 whole square. So this is the graph that we get. For this one, now let me visualize. If this is the last function or error function that we are using, then it is generic. Okay. It can be x minus 2 whole square or x minus, basically you need to imagine y here, y minus y pred. Okay. So in place of y, I am writing x here because it follows the same convention. And there y is the variable. So it can be x minus 2 whole square or x minus 5 whole square. It can be anything. Generic equation. It will shift somewhere here or here. That is what it happens max. So what we do is usually, so let us say you have started off somewhere here on the last function. This is last function, we call it as generic. For example, if I am doing y minus y pred, y minus y pred I am writing. This is error, right? If I do that for a given data set, it may follow a generic function or generic pattern, which we call it as error function or loss function. It is important terminology, loss function. So in any machine learning algorithm or deep learning, we try to minimize this loss or loss function. They may look, for in case of regression, it is a parabolic, that parabolic loss function that we use. And why we came up with this parabolic loss function? Because of the reasons that I explained earlier. If I consider y minus yp, there are chances that when we do that complete batch error calculation, there are chances that it may become zero at the end. But even though it is not zero for each and every. That is one reason. Another reason is this y minus yp, it is not differentiable at that particular point, that cusp. We need the loss function to be differentiable at each and every point. That is another observation, the reason why we don't use simple error. Rather, we use squared error, y minus y pred whole squared. So here, if this is the loss function, let us say we had started here, somewhere here. That is y value of around 5, let us say. Then to minimize, just one thing that you need to keep in mind as of now is this curve is representing loss. This curve that you see here in red color, it is representing loss. That's all. So your ultimate goal is to minimize the loss. So if you are here, where would you move yourself? You will move in this direction or in this direction to minimize the loss. If this is the curve that is representing the loss or the error, and you are here right now, at this point, let us say. Then to minimize the loss or error, whether you would move in the rightward direction or in the leftward direction. Obviously, you need to move in the leftward direction, right? This is the correct choice, not this. Why? Because here, if you move in this direction, that is in this direction, you are coming down in the sense the error is reducing. The curve is coming in this direction, right? If you move in this direction, the curve is moving in the, this is the error, in the increasing direction of error. And this is what the gradient descent says actually. So one more thing you might have seen in your school days is gradient is nothing but the slope. Slope is a vector quantity. Slope or gradient. This is a vector quantity. So what is a vector? It will have both magnitude and direction, right? So magnitude, you know. How do we calculate the slope? Magnitude? It is how much this function changes. If I change this function x value by a small amount, that is what is slope is, right? So how do we calculate it? It is something like this. Let me clear all of it. Slope, how do we calculate? Let us say this data point, this is one data point, and this is another data point. For this data point, it is around 2, 4, 6, 8, 10. So this is 2, 4, 6. X equal to 6 here and y equal to 20. And for this data point, it is almost close to, let us say, this line. So I am considering it as 8. And x is 8 and y is 30. So here, somewhere here in between this point, the slope, how do we calculate? M equal to 30 minus 20 divided by 8 minus 6, right? So 10 by 2, that is 5. Usually we don't consider the points which are this much, this far. We consider very small increments, but it is 5. So 5 is the magnitude that we got. But what is happening here? Why? What is the direction? So when we move from this point to this point, what is happening to y? It is increasing or decreasing? It is increasing, right? So we say that the slope is positive. And what is increasing slope? That is this direction. So at this point, the vector is, what to say, is in the upward direction, and its value is 5. That is how we calculate slope. So if we move in the direction of increasing slope, if we move in the direction of gradient, then we will never minimize our loss function. In this particular case itself, you can see, if we move increasing direction of slope or increasing direction of gradient, we will never minimize the loss. We will never minimize the error. We need to move in the decreasing direction of gradient. That is what is gradient descent. Descent in gradient descent says you need to descend the gradient. You need to move in the opposite direction of the gradient to minimize the loss function. If you don't remember this one, only thing is what you need to think always is there is a very what to say, this kind of loss function, very complex loss function that you have. So at each and every initialization, you will just check only one point. That is, what is the direction of slope? Whether it is in this direction or in this direction. If it is in this direction, then I will move in the opposite direction so that I will reach the minimum point at one point. Again, at this point, I will check whether the gradient is positive or negative. I will check if it is positive here in this direction, then I will move in this direction. So that is what I am doing here right now. So at this point, I check the direction of gradient is upward. So I will have to move in the downward direction so that I will reach the minimum at some point after some iterations. That is what is gradient descent is. So gradient descent tells us this is the first point. Another point is there. I will add it later. But is this point is clear to you? Very important thing. Very important basic in basic understanding should be there for this point. Gradient descent in AIML. Almost every model uses this. So don't get confused with what is this curve is representing everything. Just for now, assume that this is the loss function that you have. And how does this loss function look like? It is a parabola with minimum value at some point here. So your ultimate goal is when you initialized the weights, there is some error. It can be here or here. For example, if you are here, then you can say that obviously the gradient will be in this direction. And then, sorry, in this direction, upward direction. And then you need to move in the opposite direction to reach the minimum. That is what you will do. That is what is gradient descent is. So since it is a important point, I want to give you some time to digest it. Maybe I will share this one that I was checking, data camps link. Go through it once. If you have any questions, please ask now, or else at least in the tomorrow session. This is a very important concept to understand. Yeah. Any questions right now? So that is how we adjust the weights. Now everything is clear to you. We initialize the weights, that is for this particular use case, y equal to ax plus b. So here our ultimate goal is to get this a comma b. Those are the weights or the parameters. So we initialize with 0.1 and 0.2, let us say. So then we calculate what is the error. Here x is for first data point. For first data point, here you can see it is 1, right? So 0.1 into 1 plus 0.2. How much it is? 0.1 plus 0.2, it is 0.3. 0.3 is our prediction for 20. Actual value is 20. So what is the error? 19.3. Similarly, we do for the remaining also. But for now, let us say we are following this one, stochastic gradient. We are adjusting the weights for each and every data point. So what we do is, here, we need to minimize the error function, right? So we need to calculate the gradient first here. How do we calculate the gradient? That is dou L by dou W. That is, you might remember this one, dy by dx is the slope of a curve y equal to something, anything. Let us say if the line equation is y equal to mx plus b, then what is its slope? How do you calculate its slope at any given point? That is dy by dx, no? Dy by dx of y equal to mx plus b. That is d by dx of mx plus b. This is what it is, right? Y equal to mx plus b. So how it would be m. This is the slope. This is how we calculate the slope. So same thing here also we can do. And if it is single independent variable, we can do this. But if y is dependent on multiple independent variables, then we use dou partial derivative, dou y by dou x1 or dou y by dou x2. This is what we follow. If you want, you can spend some time on this one as well. We'll continue with the it is done. Training is done. We'll continue. I'll make it more clear by calculating for each and every data point tomorrow. Any questions you have? Intentionally, I am going slow so that this is important point, topic at least. Any questions, or you didn't understand anything?
Nageswar, when can we get the recordings to go through it again?
uh, I'll check with them. I think they should be sharing it every day. You have not yet received any recordings?
Not yet.
Okay, I'll check with them once.
Thank
Yeah, I will. Okay, if no questions, then we will stop here. We'll meet tomorrow. Thank you.